Welcome back, Focus learners, to another explainer. I am absolutely thrilled to get into today's topic because we're looking at industrial automation through a completely fresh, frankly, fascinating lens. We're going to treat a modern plant's control system, specifically the SMODIC PCS7 architecture, exactly like a living, breathing, evolving organism. Just think about it for a second. A factory has a central brain, it has a rigid legacy nervous system, a highly adaptable modern nervous system, and crucially, it has its very own immune system that actively fights off crashes. So get ready because we are about to unpack the complete biological blueprint of industrial automation. All right, let's just dive straight into this master blueprint. What we're looking at here is the macro view, the complete anatomy of our system. Notice how the data naturally flows outwards. Right there in the center, you've got the processor node, the absolute core brain of the operation. And from there, the pathways branch out into the legacy field network, highlighted in violet, and then they sweep forward into the modern industrial Ethernet, colored in green. Seeing it from this bird's eye view, you get a perfect sense of how a modern plant physically maps its data pipelines, from the central processing unit all the way down to the tiny sensors and valves out on the factory floor. Now, to make this incredibly complex system digestible, the configuration lifecycle follows a really strict four-phase structural hierarchy. We literally build this organism from the inside out. Phase 1 is setting up the brain, the core automation system. Phase 2 connects that initial legacy nervous system, known as Profibus, DP. Phase 3 introduces the modern high-speed nervous system, Profinet.io. And finally, Phase 4 establishes the plant's immune system, the vital diagnostics and health protocols that act as the ultimate safety nets to prevent catastrophic system crashes. So here's our master roadmap for today's explainer. We'll start with this system blueprint, move through the core setup and legacy Profibus, explore how Profinet breaks physical boundaries, map the physical reality of the factory floor, look into crash prevention, and finally reveal the incredible power of unified engineering. Let's kick things off with Section 1, Core Setup and Legacy Profibus, the rigid nervous system. What's actually super interesting here is how the brain's rhythm is mapped out. You see, the CPU doesn't just process data randomly, it completely dictates the flow using specific organization blocks, or OBs for short. Think of these kind of like pacemakers. Process image partitions, the PIPs, are parameterized strictly to cyclic interrupts, like OB32 and OB33. So PIP2 maps directly to OB32, PIP3 maps to OB33. And this strict mapping, it's completely non-negotiable. It ensures an absolutely predictable rhythmic behavior across the entire plant control system. Without this steady rhythm, you literally just have chaos. Building outward from the CPU, we hit the legacy field bus, Profibus, DP. Now this is an older serial line architecture, and because of that, it's governed by some incredibly rigid physical rules. Just look at the segment limit. There's a hard cap of exactly 32 nodes, and that includes both the master and the devices on a single physical line, which has to be capped at both ends by active terminating resistors, just to prevent signal reflection. Expand that out to the whole network, and your absolute maximum capacity is 126 nodes. It's a robust system, for sure, but it is heavily physically constrained. But here's the real kicker. Those physical limitations aren't just about cables. They're about identity. With Profibus, a device's identity is completely hardwired. Imagine having to literally flip tiny mechanical dip switches on an interface module to set a physical address. Then, the configured addresses in your software absolutely must perfectly mathematically match that hardware. If you misconfigure even a single tiny dip switch manually, the brain simply cannot talk to the limb. There is zero room for error here. Which naturally brings us to a really fascinating question, right? If this legacy Profibus system functions reliably, and it does, it's run massive factories for decades, why go through the massive hassle and expense of abandoning a system that already works? What exactly is the catalyst for the plant's evolution? Well, the answer is right here in what I like to call the ultimate diagnostic showdown. Profinet.io isn't just a simple upgrade. It is a totally necessary leap to shatter that serial ceiling. Let's look at the numbers. Profibus tops out at 12 megabits per second. Profinet, it delivers a massive 100 megabits in full duplex. Profibus is physically restricted to 126 nodes total. Profinet is virtually unlimited, easily handling up to 256 devices per controller. Plus, we're completely ditching those physical dip switches for purely software-based addressing. It's a massive paradigm shift from rigid physical limits to incredibly flexible digital potential. Moving right along to Section 2, Breaking Boundaries with Profinet, the modern nervous system. Okay, so to actually speak this new Ethernet language, we first need to demystify its highly specific terminology. We're talking about the XPR syntax. In the Profinet architecture, absolutely every connection point is rigidly identified. X is the interface, starting from 1 in ascending order. P is the specific port on that interface, and R designates if it's a ring port used for redundancy. I know it sounds super technical, but honestly, it's just the exact mathematical coordinate system the plant uses to know precisely where its digital nerves connect. And this perfectly illustrates how Profinet identifies itself using those exact coordinates. Unlike the manual dip switches we saw earlier, Profinet uses logical software addressing. Think of it kind of like a two-key startup sequence. At the base level, every single piece of hardware has a factory-set, permanently locked MAC address, but the system can't route logic just using the MAC. So key 1 is a logical device name, configured right in the software. Key 2 is an IP address. Once the I/O controller matches the name on startup, it automatically assigns the IP address to that specific device, which essentially unlocks true TCP/IP communication. The software literally defines the hardware. All of this builds into a seriously efficient configuration flow. Here's the exact step-by-step logic an engineer follows. Step 1, insert the Profinet I/O system to the controller. Step 2, drag and drop the specific I/O device node from a catalog. Step 3, define that unique device name we just talked about. Step 4, route it to a dedicated IP address. But it's Step 5 that is the absolute game changer, enabling swap logic. This specific checkbox allows for device replacement without an exchangeable medium. Hold on to that thought, because we are going to see exactly why it's so incredibly powerful in just a second. Let's move into Section 3, mapping the physical reality, creating the spatial map. Okay, just take a good, hard look at the physical reality of unmanaged cables. I mean, it's a nightmare, right? Total visual chaos. If a fault happens in that spaghetti, you are in serious trouble. But compare that to the pristine Pcs7 topology view. By utilizing that XPAR syntax we learned about earlier, the software creates a mathematically precise, completely logical map of every single port and cable. It visually interconnects the precise interfaces, it calculates exact cable lengths, and it syncs the offline project perfectly with the live, breathing plant. And that perfect topology map unlocks what I love to call the magic trick of Profinet. Because the topology maps exact physical ports based on neighborhood relationships, you get incredibly fast healing. Let's say a field device physically burns out on the floor. A technician removes it, grabs a totally blank, unprogrammed replacement straight from the factory, and just plugs it right into the exact same physical port. The CPU instantly recognizes the physical location based purely on its neighborhood map, automatically pushes the correct IP and device name down the wire, and resumes traffic. The plant effectively heals itself. No dip switches, no manual programming on the floor. It is absolutely brilliant. Next up, Section 4, Diagnostics and Crash Prevention, the plant's immune system. So what actually happens when things go wrong on a macro scale? First, the system constantly checks its own pulse using something called the watchdog limit. Every device exchanges data on a super strict base interval. If an I/O device misses too many of these rhythmic update cycles, the watchdog faults. To prevent false alarms, especially in redundant ring network configurations, engineers have to ensure the fixed update times yield a watchdog greater than 200 milliseconds. This tiny window of time allows the network to physically reroute data around, say, a severed cable, without triggering a full-blown system panic. Now, when a fault actually does occur, tracking down the infection is surprisingly straightforward. By simply double-clicking any faulted module, the ones with a red error icon in the topology view, the engineer queries the CPU's internal memory, and the CPU immediately fires back a precise, chronologically ordered text log called the diagnostic buffer. You don't have to guess. The brain tells you exactly what command caused the fault and precisely when it happened, literally down to the millisecond. But the ultimate safety net really lies in how we handle total crashes. By default, if a piece of hardware totally fails, like an entire I/O rack just dies, it triggers what's called a CPU stop status. The entire factory literally halts. But to prevent this, the SIMATIC PCS7 system utilizes background error organization blocks, specifically things like OB86. When a hardware error plunges down, OB86 swoops in like a safety net. It intercepts the error, logs it securely into that diagnostic buffer, but most importantly, it keeps the main CPU safely running in run status. The plant keeps producing while the engineers go fix the broken limb. Finally, we arrive at Section 5, the power of unified engineering, the aha moment. It is honestly amazing how beautifully this architecture synthesizes every single thing we just talked about. On one side, you have legacy DP, hardware addressed, serial bandwidth. On the other, modern PN, software configured, spatial Ethernet. These are immensely different physical realities, yet the true power of PCS7 is unified central engineering. The central CPU completely abstracts both of these entirely different networks into a single, standardized unified process image. So whether a failure happens on the legacy token ring or the modern Ethernet switch, it's caught and handled by the exact same centralized diagnostic logic, OB86. Old and new hardware perfectly harmonized in one single digital brain. So, to wrap all this up, here is your definitive configuration reference map. Phase 1, establish the brain's rhythm by mapping process image partitions to cyclic interrupts. Phase 2, connect the legacy DP, ensuring your hardwired DIP switches perfectly match your software. Phase 3, deploy modern Profinet by establishing TCP/IP communication and logical device names. And Phase 4, enforce spatial and health rules using the topology editor for automatic healing and error OBs to intercept stop faults. That, my friends, is the complete biological blueprint of a modern plant. Which leaves us with a truly provocative thought to walk away with today. If these incredible industrial control systems can now mathematically map their own physical space, instantly diagnose their own illnesses, and seamlessly heal their own hardware through physical neighborhood recognition, what is the next frontier for human engineering on the factory floor? Where do we possibly go from here? Keep that in mind as you look at the automated world around you. Thanks for joining me on The Explainer. Keep learning.